Started with our inaugural case study. So please welcome Dr. Qing Wang, who leads efforts at Google focused on computational fluid dynamics and building high-performance scientific computing libraries. Take it away.
Thanks for the introduction, Naomi. Now, can I share my screen? Can you all see my screen?
Looks good.
Yes.
Okay, so I'm gonna enter the present mode. Does it still work? So usually at Google, we use different where that's developed for at Google. So can you all see my slides?
Yeah.
No problem.
Cool, thank you. So yeah, thank you everyone for joining me. And my name is Qing Wang from Google Research Department. Today, I'm going to talk about some of our work down at Google for the wildfire simulations using TPU that's available on Google Cloud platform. So in this talk, I will be first beginning about talking with a brief introduction of the TPUs on Google Cloud platform. Then I'll be talking about the computational fluid dynamics simulation framework we've been implementing using TensorFlow in detail, including their governing equations, the implementations, and some of the analysis we've done for the solver. And moving forward, I will be sharing some of the details of our simulations for the wildfires. So to get started, so TPU is one of the unique features on Google Cloud Platform, which is a customized design machine learning ASIC that empowers many of the Google products already, like the translate the photos, the search assistants, and Gmail. And what I'm showing here is the version 3 TPU architecture. And from the top, you can see that there's on each of the, on top is a TPU chip. It has 2 cores. And on each core, there's a 16 gigabytes on-chip high bandwidth memory. And within each core, there's also what we call a matrix multiplication units, MXU, that performs a direct matrix multiplication of 228 square matrices. This is some special, very special feature for this TPU and makes the matrix because we can do this matrix multiplication in one single instruction. This makes us very appealing in both machine learning and the scientific computing. So going forward for some of the architectures, and within each TPU chip, there's 2 cores, and 4 such kind of chips forms a tray, what we call a tray. And then for if we have 256 such kind of trays, we call it the full pod. So in total, there are 1024 chips within a full version 3 TPU pod. And in this full pods, the 1024 chips are connected with high-speed, low-latency, 2-dimensional intercore interconnect networks. These networks are very efficient in doing the communication work. And this makes the feature, the TPU, very appealing for scientific computing because we do have to do a lot of communication between cores to exchange for the boundary conditions. So in our to simulate the wildfires, we implemented a full 3D Navier-Stokes equation in incompressible form, which is shown by the 2 equations here. And in addition, we implemented additional multi-physics models, such as the thermodynamics models with the Clausius-Clipper equation to account for the phase transitions. We implemented the combustion models for both gas phase and solid phase reactions. And also we included the capability for modeling complex geometry with immersed boundary method. So here shows how we implement our CFD solver. Well, the entire simulation framework is implemented using TensorFlow, and the numerical operators are defined with basic TensorFlow operations, such as the convolution 1D, which appears very commonly in machine learning neural networks. And to best utilize the efficiency of the TPU, we adopt a unique feature for the data structure, which is inhomogeneous for a 3D tensor, where we choose as a Python list of TensorFlow tensors. The TensorFlow tensor is a 2-dimensional tensor that represents the space in the horizontal direction, which is the X and Y direction, respectively, and the list directions along the Z direction, which is the vertical direction in the 3D tensor in a fluid flow. And the 2 snippets code shown here are for the basic building block kernel, what we call kernel functions that used to realize the finite difference operations. And in the first block, we're showing the kernel operation in the X and Y direction. In the second block, we're showing the operation in the Z direction. You can see the difference between these two. As I said, we treat it differently to fully utilize the efficiency of the TPU architecture. And because this is a graph-based TensorFlow approach, we have to first generate a graph, then serve data into the graph to do all the computations. And the two graphs shown besides the snippet of code shows how the actual code looks like in a graph view. So one thing I'd like to point out here is all our computations for the CFD framework is performed on the TPU. And the CPU is only used to compile the graph and then distribute the graph, replicate the graph over all the TPU cores. And also it serves as the data input and output. Other than that, all the computations are performed on the TPU only. And this flowchart on the right shows also our algorithm to solve this low Mach number variable density Navier-Stokes equation. At each time step, we first make a prediction for the transported scalars. Then we use these scalars to update the density. With that, we adopt a predictor-corrector approach to solve the momentum equation. With this, we first solve for the momentum equation to get a prediction of the velocity at the current time step. Then we solve the Poisson equation for the pressure correction and use that to enforce the mass conservation in the velocity field. And we repeat this entire A to F steps within each time step for multiple times to make sure that everything is consistent. So to validate and verify this solver, we perform various canonical simulation cases. And what I'm listing here is 4 of the cases we considered, which are the 2D and 3D Taylor-Grand vortex case, and the homogeneous isotropic turbulence case, and the turbulent planar jet case. We compare our results with the literature and also some experiments where we see good agreements so that we have base confidence over the accuracy of our solver. So some more analysis, and we perform a mesh convergence analysis, and we show that the overall convergence of our solver is between 2 and 3. But we also observe that the convergence rate is affected by the floating point precision. As you can see from the figure on the right, when we further reduce the mesh size at some points, the area is actually increasing. This is because with very small time step, the floating point runoff area dominates the truncation area of the numerical scheme, where we show that, well, this is due to the design of the TPU hardware. The highest precision for the TPU support to support efficiently is 32-bit. So we do have to account for this machine precision in our simulation. And fortunately, we perform based on our our analytical analysis, we figure out a rule that can guide us to prevent this loss of mesh convergence. So with the rule I specify as shown here, we can guarantee that we always fall within the region of the correct order of convergence. So further, we perform a scaling analysis for our solver, and here what I'm showing is the results for the weak scaling. And in terms of the weak scaling, we take a problem of fixed size of 1024 times 1024 times 36 on each TPU cores. And the table and the figure on the right shows the results for the scaling analysis. From the table, we can see clearly that the wall clock time per time step stays almost like a constant as the number of cores increases from 1 core all the way to a full pod. So this indicates that the weak scaling shows a linear speed up. And the linear weak scaling implies that with the same mesh resolution, we are able to solve a larger problem without sacrificing the efficiency in time. And in the next here, what I'm showing is the results for the strong scaling. And in doing the strong scaling, we choose the total problem size of 256 times 256 times 16,000. And because of to fully utilize the efficiency of the TPU hardware, we partition along the Z direction, which is, if you still remember, which is along the Python list direction. So in this study, we found that a superlinear scaling is observed for our solver. And there are mainly 2 reasons that causes the superlinear behavior. First is that we see that the communication cost is minimal versus the computational cost, as shown by the bar chart here, where all reduced broadcasts and collective permutes are accounting for the communication cost. This is also some of the appealing feature that brings out by this highly efficient ICIs. So the second reason is that we see there's less computation as the number of cores increases. This is due to the compiler optimization when we increase the number of cores. So with this, I'd like to switch gear a little bit and talk about the wildfires. So why are we interested in the wildfires at all? This from the report of the U.S. Forest Service, we can see that there's more than $200 billion loss and almost 1 million residences lost every year due to the wildfires. Just while we were talking, the Dixie fire is still on burning, and this fire has been lasting for a full month. And the ash from the fire travels more than 1,000 miles and all the way to reach Salt Lake City. And this makes Salt Lake City one of the dirtiest city around the world right now. And also due to this Dixie fire, there's more than 5,000 residents being under the execution order. So this is a tremendous economic loss caused by this kind of wildfires. And additionally, or what I will say is more importantly, the wildfires has a very significant impact on the climate. For example, for CO2 release, there's around 8 billion tons every year CO2 release due to these wildfires. And this accounts for around 10% of the annual CO2 release emission globally. And also there's a soot that is a significant health and respiration concern, and also fire aerosols. And as shown by the statistics, more than 300,000 premature deaths are caused by these fire aerosols every year. So to simulate these wildfires, we have to augment our Navier-Stokes equation with different physics models. Here, the model we considered is a FireTech model that developed in Los Alamos National Lab. And the equation, equation of reaction shown here is a single-step reaction that combines both the pyrolysis process and the combustion process. And to simulate these wildfires, we considered the effects of chemical reaction, and also the evaporation and radiation, the heat loss due to evaporation and radiation. So the governing equations are summarized as below. For the solid phase, the three equations solving here are the fuel load density, the moisture density, and also the energy equation within the solid or the fuel. In terms of the gas equation, the first equation is the mass conservation or the continuity equation, augmented by accounting for this mass addition due to phase transition. And the second equation is the momentum equation, and third equation is the energy equation, and the last equation is what we call transfer equation for the oxygen mass fraction. So one of the fire cases we considered is a Priest-Quack fire that is performed about 3 years ago, called FireFlux II. This, as shown by the video on the right, this is wildfire propagating on very flat grounds topped by homogeneously distributed tall grass. And with our simulation, we first validated our simulation against their experimental results. And the figure on the bottom right shows where they located different type of sensors. The sensors can collect information for the temperature, the wind speed, and also the pressure. So by validating our results, simulation results with the experiments, we get a basic confidence over our modeling capability for the solver to simulate complex wildfires. And based on this, we perform a series of parametric study, including all the parameters listed below here, to generate a data sets for machine learning, to train machine learning model, and also to study the behavior of the fire in detail scientifically. So some of the parameters we included are like the inflow wind speed, the fuel load, moisture content, the slope of terrain, and inflow direction with respect to the line ignition, and also the fuel type and distribution. So here, this table gives a summary on the physical conditions in our simulation, and also this is the base condition for the experiments. in the experiments, we found that the inflow wind speed is around 8.5 meters per second. This is around the higher end, towards the higher ends of the typical wildfires. The inflow wind angle is found to be at perpendicular to the line of ignition in the original setup. So in terms of the combustion models, we take the tall grass as our fuel type, and the fuel low density is recorded from the experiments as which is equivalent to about 0.5 kilograms per meter cube. As I said, as we see previously, the fuel is distributed homogeneously, and the fuel height is around 1.35 meters. So in terms of evaporation, we consider the grass as dry grass, so the moisture content is about 18% of the fuel load density. Here we also accounted for the interaction between turbulence and radiation, so the coefficient for this closure term is 1, setting to be 1. And in this table summarizes our simulation conditions. So the domain size we choose is 1 kilometer along the wind direction and 500 meters along the spanwise direction. And the height of the domain is 600 meters in order to account the full atmospheric boundary layer. So we partition this entire domain along the vertical direction. This is because we want to have a finer resolution in the vertical direction to get a better resolution over the atmospheric boundary layer. So first, what I would like to show is our comparison or validation of our simulation results against the experiments. As we can see from the left panel, we see good agreements between the simulation and the experiment for the fire topology, where we see that the fire is mainly propagating along the wind direction, and also it expands in the spanwise direction too. And both behaviors observed, this behavior is observed both in the simulation and the experiments. On the right panel, what I'm showing is the temperature profile that has been recorded at the location of what they call the main tower. So there are the temperature profiles are recorded at 3 different heights, namely the 6 meter and 10 meter, 20 meters above the ground. From this temperature profile, we can see that the rate of propagation for the fire is correctly captured by the simulation, and also the magnitude of the fire is also is correctly predicted by the simulation too. So now I would like to talk about 4 of the parameters we selected in the parameter list in our parametric study for the wildfire. The first parameter I'm going to show here is the fuel load. Here I'm showing about 3 different fuel loads, that is 0.2, 0.6, and 1 kilogram per meter cube. And 3 different rows shows the temperature, the fuel load density, and the moisture density. So from this results, we can see clearly that there's some the fire propagates slower if we increase the fuel load. This is because there's more residence time for the fire to burn if there's more fuel available behind the fire. So and the second parameter I'd like to show here is the moisture content. And this is another interesting finding is we can see clearly that the temperature drops faster when we have more moisture in the contents, which is on the right-hand side, very right column here, as compared to the left column, as a result of the heat loss. So the fire propagates slower when we have more moisture content. And some of the interesting results is what we see when we change the inflow wind speed. So the wind speed I'm showing here is from left to right is 2 meters per second, 4 meters, and 8 meters per second. In the 2 meters per second case, we see that the fire propagates into an M shape, while in this 8 meter per second case, we see a V shape. The fire propagates as a V shape. The difference in shapes and for the 4 meters per second is something in between this 2 extremes. So the interesting part we found is for the fire behaviors is that when the wind speed is low, we found that there's some insufficient air entrainment from the mainstream of the inflow. Therefore, the fire tends to seek for air entrainments from the sides. This causes the fire propagating faster along the sides. And this can be confirmed from the contour plots in the second row, where you can also see the streamlines Well, in additional to the streamlines penetrating through the fire fronts, we can see clearly that there are streamlines penetrating the fire from the site, which creates a lot of vortices around the site of the fire. This eventually turns out will create a faster propagating fire along its site. While in contrary, in the 8 meter per second case, when the inflow velocity is high, there's a sufficient air entrainment giving to this wildfire to sustain it from burning. And we can see that most of the streamlines are aligned with the fire propagation direction and penetrating through the fire front. So, and the last parameter I'm going to show here is the terrain, the effect of the terrain. And we can see from here that it's very clear to us. All these results are shown as 300 seconds after the fire is ignited. And from the results, we can see that as the slope increases, the fire actually propagates faster. This is because when we increase the slope, the velocity of the wind speed tends to increase, and this carries the fire to propagate faster. So this another wildfire case we consider is a Tubbs fire that takes place historically in California about 4 years ago. And this fire takes place in the regions near Calistoga that burns about 40,000 acres. So here shows the computational setup of our simulation. And the red box drawn on the map shows the computational domain, which is 80 kilometers long along the streamwise direction and 40 kilometers wide. This little red spark shows where Calistoga is, and this is also where the place the fire is first being spotted. So on the right-hand side is where the fire is propagating to, which is Santa Rosa. So in this simulation, we use mesh of 2048 times 1024 times 1024 mesh, which give us more than 2 billion meshes. And the resolution here is 40 meters in the spanwise direction, and we use 2 meters to capture the atmospheric boundary layer. And for this to simulate this fire, we use 512 TPU version 3 TPU cores, which is a quarter of the full pod. So the mainstream wind is blowing from Calistoga perpendicular to our domain and at a speed of 10 meters per second. Here, this video shows our simulation results. In our simulation, we found that the entire duration of this fire is around 40 minutes. But in reality, we see that this fire lasts around 2 hours. So there's more than 2 times over prediction of the fire propagation rate in our simulation. This is because that we are using an idealized field property and field distribution condition, and also we assume the wind conditions in an ideal condition, and definitely 10 meters per second wind speed is definitely towards the higher end for normal wildfires. One thing I'd like to highlight here is our simulation performs around the wall clock time for our simulation is around 3.5 days. This is a run over more than 2 billion meshes. So from our knowledge, this is so far the largest and the fastest wildfire simulation that's performed on real terrain. So to summarize, in this project, we developed a high fidelity computational fluid dynamics simulation framework using TensorFlow, and all these computations are performed on the TPU platform. So we show good scalability and computational efficiency for the solvers. And we developed wildfire models and validated our results against previous fires. With this capability, we went ahead and simulated different types of wildfires. So with this, I'd like to conclude the talk, and the floor is open up for questions.
Thank you, Dr. Wang, for providing us with those really cool demonstrations of all the computation you guys have done. We have a question from Mike Norman. Do you have the option of evaluating coupling terms at 64-bit precision? Sometimes this is important for stiff systems of equations.
Yes, I do agree that. I totally agree with this point. We do have the capability for doing computation in 64 bits on TPUs, but that's through an emulated approach. So this will make the simulation about 40 times slower than what we have using single digit precision. But when we have to do, we can always switch to the 64-digit precision. Thanks for the question.
Cool. And just a reminder to everybody, if you have questions, just drop them in the chat and we'll read them out for you. I have a question. I guess I've done some programming of like different types of hardware platform before in my past, and I remember how much, say, programming an FPGA requires a really different mindset than traditional software writing. I noticed in your presentation there was a lot of like use of graphs and use of like TPU native calculations going on. I was wondering if you found that there was a similarly like new TPU programmer mindset that you needed to adopt. And if so, what are some like resources that we can find to practice that TPU mindset ourselves?
So basically I would say the biggest difference between CPU and the classical hardwares like GPU or CPU is that there's all the most efficient computations are done by this MXUs. So it's matrix multiplication units. So whenever we consider about the problem, we'll try to convert our mindset into this matrix multiplications. And also we will try to fit our problem size as 128 squares as much as possible. That's why in the simulation domains, you can see that I always divide the domain into a multiple of 128. So this just to fully utilize this matrix multiplication units. So I believe this information is publicly available online at Google Clouds on the Google Cloud website. So yeah, definitely you're right. But have a better understanding of the hardware will help you to develop more efficient code to run on the hardware. Yeah, this is just one of the examples we can fully utilize this. And also another point I'd like to point out here is we have very fast intercore interconnect, and we can take a fully utilization of this feature as well to do communications.
It's really exciting. And so we can get access to TPU hardware by using Google Cloud Platform?
Yes.
Oh boy. Cool. So we have another question. Let's see. Do you have plans to make this model available for exploratory thinking, for example, to the Forest Service?
For sure. Actually, we are having a lot of external collaborators right now. This project is still in the beginning of this stage, so we are reaching out to different parties and to seek their advice and seek for possible collaborations. So stay on tuned.
Exciting. Well, thank you for all of the work that you're doing with this stuff.
Yeah,
as a
thank you.
current resident of California, I really appreciate it.
Yeah, thank you for having me.
Do we have any other questions in the chat for Qing? Well, I think that sounds like people are just very, very happy to see your work and that it's being done. So thank you again for coming and presenting with us today. So
thank you.
Let's see. Our next presentation is going to be at 10:45. And until then, encourage you to take a break, breathe some fresh air, and take care of yourself.